Well, hello and welcome. It is this point in your academic journey through chemistry that we're going to go over calculating energy and specific heat capacity. So what is a specific heat capacity, right? So specific heat capacity is the energy. I'm going to put a Q there. That's going to come back in a second. Needed to change 1 gram of a substance (1°C). Okay, and this is that's a mass number. We show mass with M in a formula, and we show temperature with a T. Uppercase or lowercase, doesn't really matter. So, that's what this is. Now, specific heat, the letter we use for that is actually a lowercase c. It just is. Don't ask me why, I don't know. I could probably look it up, but you could also look it up. So, you know. Anyway, so what we could do is take these words and put them into a formula, right? So we're trying to calculate C, and we said it's the amount of energy needed to change 1 gram, so a certain amount of mass, a certain amount of temperature. Now this is temperature change, and so in this case it's 1°C. But ta-da, here is your equation. Now, you've probably seen this equation. That probably looked real awkward. It felt good though. So, we've seen these variables in the energy equation. This is just the energy equation rearranged. This is your energy equation, where energy is the amount of mass, its specific heat, and how much its temperature changed. But this is all multiplied. So these are two different versions of the same formula. So let's get some practice using these. Now I've got a chart here that's already got some specific heat. That's for when we calculate either energy, mass, or change in temperature. But let's break these down. You know, let's talk about it. Well, let's talk about some numbers first. So we have 4 substances up here. I picked those off the internet. Water, I picked that one on purpose from our stuff. And then some other metals. What we see is that water has a higher specific heat than, let's say, like all of these metals by at least, like this one's 10 times, maybe 20 times, and 5 times more. So water requires more energy. That's what this means. So let's go over this. So since water specific heat is higher, it requires more energy to raise 1 gram of it 1°C. So it takes more energy to change water's temperature. That's why if you grab a cup of water and you hold like a handful of change. You guys ever hold a handful of change and then like the change is real warm after you hold it? But you can hold like some water for like 30 minutes and it's not like the temperature of your hand or gross or anything. But also like put the water down. Like don't hold it for 30 minutes, it's weird. So that's what I want you guys to think when you see a number. This is how much energy it takes to change its temperature. Alright, let's get rid of these. Let's think up some practice problems to get our heads around using this and calculating. I'm going to leave the base equation up right here because this is the father formula, the mother formula, parent formula. It's the formula. We just, I don't know what to call it. Anyway, we burnt some Cheetos, and by we I mean Miss Littrell and Mr. Schartzer, and by some Cheetos I mean one. I actually got to eat the rest. So it's a good year. We didn't have to burn all the Cheetos. It's good for you because you weren't here to watch me eat the Cheetos because I would have eaten them in front of you. Anyway, and we were calculating how much energy was released by the Cheeto by figuring out how much was gained by the water. So we were using water, right? So we said, let's say that we have that our water was about 70. So let's start, plugging and chugging, as the math teachers say. Energy. So we've got MC delta T. I like to rewrite it every time I do a problem. It's just one thing that I do. And then I substitute. So let's say that we had 70 grams of water. I think it was like 69.1 if you did the assignment, but it was supposed to be 70. We look at C comes from our chart. So this is the C chart, okay? So, it's got 1. Very good. That's 1 calorie per gram degree Celsius. Now, another thing that you should do every time you do math in this class is that you should put the units. Why? I'll show you a cool trick in a minute. And by a minute, I mean like probably 4 seconds after I write the change in temperature. Now, we know that it started, so this is also, just to show a further thing, T final minus T initial. So you take the final temperature minus the initial temperature, and that'll give you the change. For simplicity's sake, let's say that it went up, let's pick a number. What's a cool number? Let's do 20 because then I don't need a calculator. 20 degrees C. Okay, so now we've got all the things. It's time to plug the numbers in, right? But wait, let's make sure we did this right. So our unit for Q, what we're looking for, we're going to find that, and it's going to be calories, right? And so let's see if our numbers that we plugged in, which I know I did, I plugged in the numbers because they came off my brain and I did the right ones. I didn't pick wrong ones. But to make sure that our numbers come from the right spot, let's double check. So we've got, let's look at our units to see if it comes out the calories. Because when you do math and chemistry, you should always do to the units what you do to the numbers. So if I want to multiply all these numbers, I need to multiply all the units as well. So we've got grams, and then we've got times calories per gram. So since it's a per gram here, the grams cancels out with the per grams. And then we've got also per degree Celsius, and then times Celsius. Those also cancel out. Calories doesn't cancel out. Good. That's what we wanted. We know we got the right answer. We know we multiplied at least the right types of numbers for this equation. So now we do 70 times 1. That's 70. And then we've got, 7 times 2 is 14, and then 2 zeros, so that's 1,400 little c calories. So that's how much this theoretical anything that was burnt under the water, that's how much the water absorbed. was this much. So we can assume that it's from whatever we burnt underneath the water. Let's pretend that we took the same amount of energy and that we applied it to, which one do you guys want to pick? Everybody just shout out whichever one you want to do. Okay, fine, we'll do cobalt. I don't know why you picked that one, but I hope you guys think this is as funny as I do. Alright, so let's apply this same amount of energy, but to cobalt. And let's figure out how much its temperature would change. Okay, so we're not going to know its starting or its final temperature, but we will know how much it changed in temperature. I mean, we can make up a starting or an ending and then find the other one by subtraction. So let's calculate the temperature change. So now to do this, you guys should have had algebra by now. Whether you're good at it or not, different story. But this is it's not actual like algebra. It's just solving a multi-step equation. Anyway, so we've got 1,400 calories. That's what we know. How much will 1,400 calories change the temperature, squeeze of right there, of, we need a mass. Let's just say that it was 70. Now I might need a calculator. Of 70 grams of cobalt. All right, cool. We've got our problem. Now we've got to rearrange this equation to work for us. We need this variable by itself. Remember that the triangle in the T, that means temperature change. Okay, that's one unit. Triangle is not separate from the T. It is with the T. Okay, so we need, so to rearrange this, we gotta get rid of these away from this side. So what we do is we divide both sides. I don't know if I'm not really qualified to teach you math, I guess. But what we could do to get this by itself is to divide both sides by MC. Right? Because then they're still the same. But now these cancel out now. Okay, good. So that's what it is. I'm gonna rewrite that so that it looks better for my purposes. So delta T equals Q divided by MC. Now we just drop our numbers in. I'm gonna go left to right on this one because there's not a lot of room down here. Okay, so Q is this number. Q is the calories number, so 1,400 calories. M is our mass, which is going to be 70. And that is grams. I'm going to put parentheses around here just to block it off so you know. And then C is going to come from this chart. Now C is not the same as it was water, or else we'd end up right back with the 20-degree temperature change. But we're not going to. This one is 0.1. And that is calories per gram degree Celsius. Okay, now, I probably will have to put this in my calculator. No, I won't. But I should. I'm going to. Let me go grab it. Okay, I'm back. Also, I walked all the way to my desk and I walked right past like the whole thing of calculators. Anyway, so how do I put this in my calculator? Now, you got to follow order of operations here, or it's really going to mess you up. It's going to mess you up bad. So what we got to do, 1400 divided by, we're going to put 70 in there. Now I'm going to put that in a parenthesis. So parenthesis 70 times 0.1, close parentheses, equals. Now this tells me, let's check this out, all right? We got a gram and a per gram on the same level of this. What is that called? Anybody know what the bar thing in math is called? Whatever. Grams cancels out when you divide by a fraction. So this is on the top, but on the bottom, but this one's on the top, so the calories cancel out. And all we're left with is going to be degrees Celsius. So we get 200 degrees Celsius. So, ta-da, voila, bing, bang. That was cool. We did math. So cobalt, because if you insert the same amount of energy as you do water, it's going to go 10 times more temperature change, because it has such a low specific heat capacity. So water absorbs all that energy but doesn't actually change its temperature a whole lot. Cobalt absorbs that energy and then will burn your fingers if you try to touch it. 200 degrees C is a lot. One time I touched a hot plate that was probably there or more to see if it was on. I burnt my finger. I hid it from my teacher. I just grabbed a piece of ice and then went to my desk. Oops. Anyway, let's calculate some more. Let's say that we found, what do you guys want to say that we found? You guys thinking like a metal, like a meteorite, some kind of unknown liquid? What do you want? Let's say that we found, let's go meteorite. Meteorite. Okay, so we found a meteorite, okay? And we're trying to figure out what it is and what its properties are. Specific heat is a property. That's what we're going to calculate. So we're going to figure out, try to figure out what kind of metal it is. So we're going to figure out its specific heat. So let's see. So you find, I'm just going to say an unknown metal. An unknown metal, and you heat it up. And you apply. I teach. I don't write these things. And you apply, how much energy do we want to apply? Let's do 1,000, because that's an easy number. 1,000 calories to, you know what else is an easy number? 20. To 20 grams and its temperature increases by 30 degrees Celsius. What is its specific heat capacity? Okay, so I used all of my board to write this question. and that was a mistake. Anyway, so let's write down what we have. What do we know? So we know we've got Q for this question is going to be 1,000 calories. We know that M is going to be 20 grams, and we know that delta T, the change in temperature, is going to be 30 degrees C. We don't know what C is. That's what we're trying to find. I'm going to erase the question now so that I should do the math in front of you. Alright, I'm going to switch marker colors, really just because. Alright, so we need to set this up, so we need C. Let's go back to the original definition from our notes that we started with. C. Wow, I don't like the color of that marker at all. Let's use red. Actually, I brought a black marker. Duh, of course I brought a black marker that's in black. Already used it and lost it and found it. Alright, so we got C. Specific heat capacity is the energy required to change a certain mass, a certain number of temperatures. Okay, so it's, yeah. So let's figure it out. Let's toss those numbers in there. So we got C equals Q is 1,000, and that is 1,000 calories. And then we've got, I'm going to parenthesis the bottom ones. That's just one thing that I do. We got 20 grams, and it changed 30 degrees Celsius. Okay, I can't do this in my head, so what I'm going to do, I'm going to show you another way. I know I'm not being very consistent and this might be confusing, but another way to do this properly in your calculator is this. We're going to do 1,000 divided by 20 divided by 30. That also obeys these order of operations and will give you the correct answer. What will not give you the correct answer is if you do 1,000 divided by 20 and then hit times 30 in your calculator. That's not it, because the 1,000 is being divided by 30, so you need to divide by 30. Okay, so 1,000 divided by 20 divided by 30. It's 1.67. Okay, now look at this. Look at, you see what I'm seeing? The units, none of them cancel out. So I got to put them all in here. So I did calories divided by grams in degrees Celsius. So here's our answer. Wow, our mysterious unknown has an even higher specific heat capacity than water. That's very strange, but I guess it is possible. It is possible. I hope that these notes, let me check my notes and make sure that I'm not forgetting anything. Oh wow, I made up a lot better numbers last time. Anyway, that ends this portion of Chemistry Notes. I'm Mr. Williams. Bye.